Thank you all for joining another lecture for Introduction to Computer Graphics. We have been talking about shading. Last week we talked about shading in general, and we talked about foam material model and blend material model, and we talked about smooth shading and how to interpolate normals so we can get smooth looking surfaces out of our polygonal shapes. And we talked about how to handle all of those mathematical details and how to transform normals. But today, I would like to talk about the concept of shading in more general terms, in the context of what is called in computer graphics the rendering equation. So today, we're going to be talking about the rendering equation. Now, what we talked about previously is sort of, we took a little bit of a similar journey to what Fong and Glenn and others took back in the days, closer to the beginning of computer graphics, when they were figuring out how to do shading and how to do rendering and things like that. And they figured all those out, and that's the stuff that we covered last time. But later on, Jim Kajia came along and came up with an equation, and he said, this is the rendering equation. And he said, this is what we've been trying to do. So he put everything that people were doing in computer graphics in mathematical terms. And still today, that very equation, the rendering equation, is the basis of all rendering done in computer graphics. People extended this concept just slightly, just a little bit, but the rendering equation, as it was presented by Jim Kajia back in 1986, if I'm not mistaken, still stays as it is, and that's what we're going to explore today, and we'll understand. We'll hopefully understand. Now, this is the rendering equation. Now, if you haven't seen this previously, this might look a little bit scary because of integral and all these funny symbols and whatnot. But this is actually not scary at all. So at the end of this lecture, you will understand this equation really well, and this will make perfect sense to you, and this will actually hopefully improve your understanding of what rendering is. All right, so that's going to be our goal for today. And if it looks scary for the time being, don't worry. That's normal, but we'll fix that. So let's put this equation on the side, and let's take a look at images. let's take a look at teapots. They're much easier to look at, right? So you remember these two teapots? We looked at them last time. So this is a teapot with just diffuse reflections on it, and this is a teapot with some specular reflections on it. Now, I want you to look at this. Now, forget about foam shading or blend material model or foam material model. Forget about computer graphics for a second. Right? Assume that these are actual, physical, real teapots. Right? I'm showing you this. Just imagine that they're real. I know that don't look that realistic, but for the time being, try to imagine that they're real. All right. So if you look at them, what do you see as the difference between these two? Like the physical difference between these two. What do you imagine when you look at them as like the surface of these two objects? When you look at this, you should notice that, obviously this one is shiny. This one is not shiny at all, right? This one is sort of make, and this one is a lot shiny. And then probably, if you were to touch this, if this was something real, and if you were to touch this, you would expect that you would feel some roughness on the surface of this one. Like if you were to put your hand over it, it would probably feel a little rough. And this one would probably feel kind of perfectly smooth almost, right? Do you get that sensation? I'm hoping that you do, because actually the material appearance is very, very important to us, because we infer a lot of information just by looking at things. So getting this material appearance right is very important for us to be able to get something realistic from computer graphics, that things looking exactly like we expect them to look, and this looking like wood, and this looking more like wood with some maybe protective coat on it, so it looks shiny, right? So this is, it has no finish applied on it, and this is like after we apply some finish. That's should look more like that. Well, we'll improve upon that just a little bit. So don't worry about it. So let's get rid of this shiny one. Let's take a look at this one with a more like a rough surface for a little bit. So why does this look rough? So let's take a look at a piece of this surface. I'm going to highlight a little piece over here, and then I'm going to enlarge that piece. So it's almost like flat, right? But if you zoom in a little bit, let's take a little piece and extend it out. You know what? Let's zoom in some more. Let's imagine that I did it a whole bunch of times. And in the end, I get a sort of zoomed in surface. But the surface, if it looks like this, I don't expect the surface to look perfectly flat like this, right? I expect the surface, if you were to zoom in enough, I would expect the surface to look more rough, like something more like this, not perfectly smooth. And this is how, if you were to put your hand over it, you would feel some roughness. And the reason why we can actually see this is because of how light reflects off of this surface. So that's what we're going to look at today. We're going to examine what would happen if I were to shine some light on a surface. Now, this is actually a very, very complicated, very complex process if you were to analyze the physics of this. Because, if you zoom in and out, you won't necessarily see a surface like where you want to see all these molecules and whatnot. So, but we're not going to get there. We're not going to get to that level. Also, when you think about light, you can think of them like you think of light as a bunch of photons moving around, or you can think of this as a wave, right? So we're not going to talk about the wave behavior of light either. So what I would like to accomplish today is just to get a more intuitive understanding of what's going on to this surface, as opposed to giving you the actual physical details as we understand it today of what happens when the light hits the surface, right? So this is not a physics course. That's not what we're trying to accomplish. So I'm trying to give you a very simplified view of what happens to light when light hits the surface, all right? So I just want to put this as a disclaimer. Don't use what I'm explaining to you as the basis of any physical understanding of what exactly happens to light when it hits the surface, right? All right, so the simplified view of this is I have some light beam coming to the surface, and when I say light beam, I mean some light rays coming all parallel, well, in this case, in this direction, and hitting the surface. Now, because this surface is sort of rough, when these light rays coming in and hitting the surface, we would expect them to scatter in all different directions. And that's really coming from the fact that the surface is sort of rough. So when this light beam hits the surface, what we would expect to see is that the light beam would scatter something like this, right? It's so chaotic, it's scattering in all over the place. And this is really a reason why we would have this light scattering happening in all directions. Now, this is a very sort of zoomed in picture of this. If you zoom out a little bit, I cannot see these individual directions and think about the fact that these imperfections on the surface are very, very small. And when I shine some light on the surface, I'm hitting the surface with really a very, very large number of photons, right? And those photons will be bouncing off in all sorts of directions. So statistically, when you look at it, and we should really look at it statistically, you would see that light is bouncing off in all directions. And if you have a perfectly diffuse surface like this one, then it won't matter from which direction you're looking at. You're going to see the same color on the surface, like whatever the color of the surface is. So whatever the spectral reflectance of this material is, that's what I'm going to see regardless of which direction I'm looking at this surface. And the reason why this is happening is that overall, statistically, the light beam that hits the surface is scattering in all directions sort of uniformly. All right, that's why it's happening. Now, what we are using here is something like we talked about this, the Lambertian surfaces. And this is like a Lambertian reflection is how this particular image was rendered. And the Lambertian reflections assumes that you have your perfect reflectance profile. The real materials are not exactly like that, but it's not a bad approximation of what surfaces look like to us. So it's actually a fairly okay approximation of what surfaces do to a certain level, of course. But this picture of surface roughness and light scattering all over the place should give you some sort of understanding of why this is happening, right? That's the goal. All right. So what if it wasn't like this? What if this surface, as I zoomed in, was perfectly flat? Now again, things are not going to be perfectly flat, but let's say it's almost perfectly flat. So much so that even when I zoom in like this, I can't quite see much. It still looks flat. Right? What would happen to light that hits this surface in that case? So light wouldn't scatter in all directions like this. So we would get something more like this, right? So we would expect the light to bounce off and preserve its directionality. Well, of course, its direction changes, but at least it's reflecting uniformly. Okay, let's say that's how my surface is. My surface is almost perfectly flat. Now, what would my teapot look like then? It wouldn't look like this, right? It would look like this if the surface was rough. If the surface isn't rough, if the surface is like almost perfectly smooth, in that case, it will look shiny. But how shiny? Actually, it will look just shiny. It will look like this. Now, you see, I'm here on the surface of the teapot. I'm only seeing the reflections of the light sources that are hitting the surface, because this is almost like mirror, and I'm not seeing anything else. Now, of course, this doesn't look quite like mirror. It looks a little bit dark, as you can see. It doesn't look quite like mirror, and the reason is that not all of the light is being reflected. A part of the light is being absorbed, right? But all the reflections are happening in the perfect reflection direction. So I can see the reflections of the light sources. I can see the reflections of much else. Well, if you pay attention, there's reflections of some other things on the surface as well. But mostly what I see is the reflection of the light sources that are illuminating the surface. Right. So if the surface is almost perfectly flat, as you zoom in, if it's almost perfectly smooth, you would get something like this. And so as I rotate this object, these shiny reflections will change their places on the surface, right? Because based on how the surface normal is changing, these reflections appear at different places. These visible reflections appear at different places on the surface. And how dark the surface is a function of two things in this case. One is how much reflectance this surface has. That is, it's not reflecting all of the light. It's actually the light energy that's being reflected is sort of reduced. So I can only see the very, very bright things that are illuminating this. So I can only see the light source. And the other thing is, of course, the amount of illumination I'm putting onto this teapot. So if it's in a dark room with a few light sources, I'm just seeing the reflections of these light sources, right? Nonetheless, I'm seeing the reflections of the light sources here. Okay, but this is not exactly what I wanted to get. What I wanted to get, well, my goal was to be able to get some shiny looking teapot like this, right? So it has some diffuse light reflection. I can see a recognizable color on the surface, and I can also see these specular highlights that are coming from almost perfect reflections that are changing places on the surface. So I would like to get something like this. So what would this look like? So this means that I have a mixture of the two. I have some light that's reflecting almost perfectly like this, and I have some light rays hitting the surface are scattering sort of diffusely in all sorts of directions. So I would expect to see something more like this, right? So as you see here, these blue ones are reflecting off of the surface specularly, and these other ones are reflecting in all sorts of different directions. So what does this mean? Well, this could mean a number of different things, actually. So this could mean that maybe my surface is not as smooth. Maybe it's a little rough, maybe. Well, maybe not so much. Maybe it's more like, parts of it is almost flat and parts of it is kind of rough, maybe. Now we could produce something like this, like a percentage of the surface is almost perfectly flat, as you can see here, and some percentage is kind of rough. So we get both kind of reflections. Or more likely, if I see a wooden surface like this, what I would expect to see is that probably I had some rough wood and I put some protective coat on it. Right? This protective coat, when it dries up, it's going to form a very smooth surface on top of that. And that's going to be transparent, semi-transparent. So light that's hitting this protective coat, a portion of this light is going to reflect off of that surface. And because this is really smooth, I'm going to see perfect specular, not perfect, but almost perfect specular reflections on this for the light that reflects off of this surface. And a portion of the light is going to actually penetrate into this semi-transparent protective coat. And the part that goes into this protective coat is going to refract into it, right? And then it's going to bounce off of the surface of the actual wood. In that case, because the wood surface is rough, it's going to scatter in all sort of various directions, almost randomly, and that we're going to see the reflections that will come out of the semi-transparent surface, and that will form this diffuse reflection. So when you look at an object like this that has some diffuse and some specular reflections, it could be all sorts of different things. In this particular case, you would probably expect something like this, right? Okay, so again, let's compare these two teapots. Like you see at the top, I have my diffuse teapot, and over here I have my diffuse teapot and some specular reflections on it. Now, after all this description, when you look at these two images, these two teapots, do you notice something wrong here? Now, let me give you the parameters of what's going on here. Let's say I have the same teapot. I took this teapot and I put some protective coating on this teapot. I just painted over it with some protective coating, just like the example I showed you a minute ago. And so I'm expecting to see some specular highlights coming off of that surface now. And I'm eliminating both of them in the very same environment. Do you see something that doesn't quite look right with our understanding of how these specular reflections are forming? The problem is with the diffuse reflections. The specular reflections they're okay, but there's a problem with diffuse reflections in this case. Here's the thing. In this case, all of the light that's hitting the surface is reflected off of the surface diffusely in all directions, and we're seeing it. In this case, and the bottom case, some of the light is reflected specularly off of the surface. Some of the light is reflected specularly. What does that mean? That means the same light that portion of the light that is reflected specularly cannot at the same time be reflected diffusely. Right? So if a portion of the light is reflected specularly, only the remaining portion can be reflected diffusely. Right? So we can't have it both ways. Right? So if I'm going to have some specular reflections on this surface, that is going to come out of something. I'm going to have to reduce the diffuse reflections. So my teapot should look a little bit darker now, right? And this looks, okay, you can debate whether or not this looks more realistic, but at least it fits with our understanding of what is happening to that surface, right? So we would expect this to look darker. And that's exactly what happens in reality. If you've ever tried this, if you took a piece of wood and put some protective coating on it that, the wood started looking shiny, it will also look darker because of that. So what's happening here is that as light hits this protective coating, a portion of that is going to reflect off, and only the remaining portion can go into that protective coating and illuminate this surface underneath the protective coating. And only a portion of that will be reflecting off diffusely, and we will be able to see it. And that's a very, very important concept. And that sort of brings us to this concept of energy conservation. We don't want our materials to reflect more light than they receive. Now, we're going to talk about this a number of times today, because that's one of the main topics of our discussion for today. So I'm going to repeat this. We don't want our surfaces to be reflecting more light than they receive, because that would be very unrealistic. Actually, that causes a lot of problems in rendering if you're trying to do any kind of realistic rendering. The surfaces can only reflect a portion of the light they receive, and if they're reflecting more light, it's like they become light emitters, right? They become light sources, and we don't necessarily want that unless the surface is fluorescent or something. But this is not a fluorescent teapot. So anyhow, let me get rid of this and show you this image. So what we're trying to do is we're trying to do some sort of shading, and when we're doing shading, this is the setup that we got, right? We have some light hitting the surface, and we are interested in knowing the color at this point. More specifically, the light that is reflected along this viewing direction. That's what we're interested in. And the surface definition, what's happening to the surface, how exactly that surface is formed, or its microstructure, if you will, is going to determine what's going to happen here, right? And this can be a very, very complex process involving, light maybe going into the object a little bit. In this case, it's penetrating into this semi-transparent layer and bouncing off of the back. But when I look at my teapot image, I don't quite see the protective layer in detail so much. It's really like this layer is really thin. So we're not going to model this extreme complexity of what's happening to that light source. But what's important for us is to statistically get this light reflectance distribution correctly. That's what's important for us, right? If you can get the statistics of how light is reflecting off of the surface, then we're going to get a surface that looks like what we're trying to model, right? So that's the whole point. So I'm going to replace all this complexity with this one function. This function that we call the bidirectional reflectance distribution function. So this function is going to give us the statistical distribution of how light bounces off of this surface. Again, bidirectional reflectance distribution function, or BRDF. So you'll hear this phrase BRDF a lot from people talking about rendering, because it's really, really essential to what we do in rendering. This is a function that will tell me it's bidirectional because it's taking two directions, right? It's taking the direction of incoming light direction and the outgoing light direction, the view direction, if you will. And this function is going to return a value that will tell me what portion of that light is being reflected, what portion of the incoming light in this omega direction is reflected along the given view direction. So that's why we have these two directions, right? And this function determines the behavior of this material. So this is our definition of how the material behaves. Right? And for most materials, this is a sufficient representation of what light does to that surface. And if you have an accurate description of this function, we can get very accurate renderings of that particular material. Right? For most materials, this is actually very, very good. So all we need is this function. Again, bidirectional reflectance distribution function, BIDF. Now, I'm going to make some changes to our terminology here, so to our notation here just a little bit, and make it a little more standard and closer to how Jin Kojia defined these terms in the rendered equation. So I'm going to replace this term V, and I'm going to sort of change the notation over here, and I'm going to change the notation I here. So notation is changing, same figure, different notation. Are you ready? This is what it looks like. All right. So now we have the incoming light direction is represented as omega I, and outgoing light direction is represented as omega O. So this is for outgoing light, it's incoming light. And the incoming light, the magnitude of the intensity, radians if you want to be more specific, the incoming light is represented as Li, and the outgoing light is represented as Lo. Okay? And of course, the theta, I put the same in I over here as theta I. It's just associated with this light source. This is a more standard representation of the BIDF function. So BIDF is going to take two directions, the incoming light direction and outgoing light direction, and it's going to return us the amount of reflectance here. Now, what is this function going to return? Is it going to return us some scalar value, some color value, some... What do you think? So it really depends on what exactly it is that we're doing with our renderer. So in general, it can return a whole spectral value. It can return a light spectrum. And that tells you the reflectance of this material properly. But at the very least, we would probably expect this to return an RGB color value, right? And it tells us the color of the reflected light. So if it's tinted in any way, and it might be, right? Most surfaces will reflect their own colors. But just for the sake of simplicity, let's assume that it just returns a scalar. And you can think about this as it returns three scalars that corresponds to RGB colors, or it returns a whole bunch of scalars that corresponds to a whole light spectrum. But just for simplicity, let's assume for the time being that it just returns a scalar value, right? Just imagine just one instance of this BRDF function where I'm going to keep this input, omega I, the input direction, I'm going to keep this constant. So it is going to be this particular vector, right? So that means the light that's hitting the surface is coming in this direction, right? So what's going to happen to this light when it hits the surface? The light is going to scatter in all directions, right? It's going to scatter in all directions. But it's not going to scatter in all directions the same amount. This reflectance in different directions is going to vary, right? So I'm going to represent it as like this. It hits the surface, and in some directions I'm getting a lot of light. Think about this as the light intensity. The length of the vector, think about this as the light intensity. So a lot of the light is sort of reflecting in these directions, and a portion of the light is reflecting in other directions. So this BRDF function is going to tell me what percentage of the light is reflecting in what direction. What percentage of the light coming in this particular direction is reflecting off of in all directions. So my light can come from all directions, of course, and in the end, it's going to scatter in all directions over this point. All directions, we can think of this as like a hemisphere over this surface. And a hemisphere of all directions, I'm going to represent that hemisphere using this capital omega symbol. Right? That's the hemisphere of all directions over this surface. Now, the important thing here is energy conservation. Let's think about energy conservation for a little bit. So if I look at all light scattering in all directions over this hemisphere, if I look at all light, if I just add all of that light, I look at all of the continuous, infinitely many directions over this hemisphere, and I add all of that light. Well, what do I mean? I mean an integral, right? If I take an integral over this hemisphere, capital omega, an integral over this omega. If I take an integral of my BRDF function over this omega for a particular omega I value, for a particular incoming light direction, right? I'm only integrating over all possible outgoing light directions. Right? What am I going to get? Let's say that my BRDF returns some scalar value. If I integrate my BRDF, what am I going to get? Am I going to get the reflected light? I'm not going to get the reflected light because I'm not saying how much light is hitting the surface. I'm telling you the incoming light direction, which is omega I, but I'm not telling you how much light is coming to that surface. So my BRDF is only telling me the percentage of light that is reflecting off of each one of these omega O directions. So if I take the integral over the entire hemisphere, over the entire possibility of where the reflected light can go, it should always be smaller than or equal to 1. Right? Because if it is greater than 1, that means if I sum all the reflected light is going to sum up to something greater than the incoming light. If it is greater than 1. It can be 1 in theory. That means the surface is reflecting all of the light that it receives. It's absorbing nothing. That would be a very interesting material, right? If it's reflecting all of the light, that could be a very, very useful material. Unfortunately, not a very realistic material. So we would expect real materials to absorb some of the light. You're going to lose some energy with this whole reflectance. So some light is going to be absorbed, some light is going to be reflected. So in general, we would expect this to be smaller than 1. Right? So this is a measure of what percentage of the light is reflecting. So this can't be 100%. It cannot be greater than 100%. So it cannot be greater than 1. That's the idea. Right? And we typically represent BRDF. We draw it as a function over this to represent how much light what percentage of the light is being reflected for each given direction, right? Instead of drawing these arrows in all directions, we typically represent a curve around this reflected surface to represent the BRDF. And if I get rid of all these reflections arrows, so this is what the BRDF function looks like, right? So there's an incoming light direction omega I. I'm fixing it. For this, and for this omega I in this 2D cross section, I am getting the BRDF shape that looks like this. Right? Of course, if I change this direction incoming light, the shape of this function is going to change as well, right? So if the light direction is something different, I'm going to get a function that looks a little bit different. So BRDF is not just a function of the outgoing direction, it's a function of both incoming and outgoing direction. So in 3D, I can represent an incoming direction in 2 dimensions. Yeah, it's a 3D vector, but it's a unit vector, so it only has 2 dimensions actually. So you can think of this incoming light direction being 2 dimensions and outgoing light direction being 2 dimensions. It's a position on a hemisphere. Both of them are positions on hemisphere. So BRDF is more like a 4-dimensional function. Right? 2 dimensions from this, 2 dimensions from that. It's a 4-dimensional function that returns either a scalar or a color value or a color spectrum or light spectrum, depending on how we're modeling our BRDF. But of course, it depends on. So this is just one instance of this cross section, 2D cross section of what the BRDF would look like for this particular incoming light direction omega I. And of course, if I change that omega I to something else, the BRDF shape is going to deform accordingly. A lot of times, so when we're doing blend shading, for example, when we're doing blend material, we're not generating this entire function, right? What we want, what we're interested in, is just one value from this function. That one value is the value that corresponds to our outgoing direction. So we are just interested in this one value here. And that's what we're trying to compute when we're doing shading. So I have my incoming light direction and outgoing light direction. And I'm going to feed it in my BRDF, and my BRDF is going to give me the output. So that's all I'm interested in. I just want to evaluate it in one instance for incoming and outgoing light directions. In most cases anyway. So this incoming direction will be associated with the incoming light Li, and outgoing direction, I will use it for computing the outgoing light Lo here, right? So before we continue, I want to tell you that BRDFs have a very interesting property. So this BRDF function, I'm writing 2 instances of it. There's a good reason for it, because I'm going to take this one and I'm going to switch its inputs, right? If I move them around, I'm going to tell you that these are equal. So this is happening because of the properties of how light interacts with surfaces and the whole geometry of what happens here. So this doesn't mean that I'm getting the same function that looks the same with the omega O and omega I. That's not what it means. But if I give you a pair of input and outgoing directions, and if I switch the order, my BRDF is going to produce exactly the same value. That means I can think of light as light that comes from a light source, hits the surface, and comes to the camera. Or I can, when I'm doing rendering, I can do the exact opposite. I can start from the camera and move from camera and go towards the light sources. Geometrically, it's the same behavior. The light behavior is equivalent. Or I can think of this as, like, I can switch the order of my camera and the light source like this. Yeah, the incoming angle is different and whatnot, but my BRDF is going to produce the same value. It's all related to how light interacts with surfaces, right? So either way, it gives you the same value. That's an interesting property of BRDFs. But what I'm interested in, actually, is computing this reflected light source, right? The reflected light. This is what I'm interested in. That's what I need the BRDF for. So all I want to know is this outgoing light in this particular direction. It's typical to write this as a function of reflected light LO as a function of the reflected light direction. Because obviously the reflected light is going to vary if I change my camera position. If I look at it from a different direction, I might get a different value, right? So the reflectance is not going to be the same. Not necessarily going to be the same. All right? So this is what I want to find out. Now, we talked about how to do shading. So you guys should have an idea about what to do here. So what do we do here to compute this outgoing reflected light? We're going to take the incoming light, right? The incoming light, whatever that is. And we're going to do our, well, if we're doing, if we're using a blend material, we're going to do, use our blend material formulation. And we're going to figure out how much light is reflecting along this direction, right? So the incoming light is going to be this term here, right? So the light, incoming light, Li, along this incoming direction omega I, multiplied by the cosine term, the geometry term. Remember the geometry term? We talked about this extensively and why it exists. Now this whole thing is just the incoming light. And I'm going to multiply that with my surface BIDF. And I multiply that with my surface BIDF, that's going to give me the reflected light along this direction. And this is exactly what we have been doing when we talked about the foam material model and then the Blinn material model. Remember, I talked about this cosine theta term being outside of the material definition. This is what I was trying to talk about. So back when Foam came up with his material model and then Blinn came up with his material model, this concept of rendering equation was not there yet. So this cosine term was sort of implicitly included in the material definition back then. That's why if you Google the Foam material model or Blinn material model, you may not see this cosine theta term as something that's outside of the material definition. You may actually see it as inside of this material definition. You may see this cosine term as a part of the diffuse term. Because this whole concept of rendering equation came about much later, and we put this cosine term outside of this material definition, BIDF definition, outside of the material definition later on. So historically, it was not in there, but this is a more proper way of writing everything. Okay, so this is what happens if I have just one light source and the light is coming from this omega I direction. What if I don't have one light source, but I have a whole bunch of light sources? What do I do now? Now, we talked about this briefly last time, if you will remember. In this case, light is coming from a whole bunch of directions, and by the property of lights, I am just going to add them, right? So the reflected light along this direction is going to be the sum of all light hitting this point from all of these light sources, and all of them reflecting in this particular omega O direction. So I can write it as a sum like this, right? Sum over all I. Now I'm going to do a sum over all light sources, and I'm going to find out how much light is coming from the light sources along their light directions. And I'm going to multiply them, of course, by their own geometry term, theta I. That's the reason why I put an I here when I wrote theta I. I didn't leave it theta I. So if I have a whole bunch of light sources, I am going to do a sum like this. Simple enough? Simple enough, right? This is exactly what we've been doing. We're just doing multiple light sources. All right. But in general, light is not just coming from a few light sources. In reality, when you look at a surface, and we're trying to imitate reality in computer graphics to be able to produce realistic looking images, in reality, when you look at a surface, light comes from all directions. So there's some light coming from all directions. I'm going to revisit this concept later on. But in a realistic environment, there is some light that's going to be coming from all directions. So you can really think of this as light coming from all over this hemisphere, the hemisphere represented with this capital omega symbol. If the light is coming from all directions, then we can really think of this instead of a sum for a finite number of directions where I have light sources. I can think of this as like an integral over this entire hemisphere surface. Like integral over the entire hemisphere omega that defines all of my omega I incoming light directions. And I'm going to find out light coming from all directions, and I'm going to do an integral over all directions. And I'm going to, for each direction, I'm going to multiply it by its cosine term and my BIDF. And that is going to give me my reflected light in this reflected direction. And now this, if you recognize, is the rendering equation. So this is what Jim Kajia defined as the rendering equation and said, this is exactly what we've been trying to do. And then he came up with a very good method for computing this for more realistic light simulation. And we'll talk about that stuff later. But for today, I want to concentrate more on the BIDF term over here. So we're going to talk about how to compute this incoming light, and that's going to be very, very important. Especially computing incoming light from all directions is going to be very, very important for generating realistic looking images. And this requires doing a realistic light simulation, so we get this term right. So if you get this term right, and if you have a realistic material model here representing our BIDF, and if you can actually compute this integral with sufficient accuracy, that's when we're going to get very, very realistic looking images. That's when we're going to get lifelike computer graphics images that would be very, very difficult to differentiate from reality. So this equation summarizes what goes on in rendering. All right, so let's try to remember what we did before. We talked about the blend foam material model, blend material model, and foam material model, and they both looked very much like this, right? So I can write the blend foam material models as like a BIDF formulation like this. So the diffuse term is just a constant term, right? So no cosine here. Cosine is out there. It's not inside the BIDF. I keep saying the same thing because when you Google this, you're gonna find this cosine term right next to this. This is not the right place to put the cosine term. Okay, the cosine term is outside. So this is a BIDF. This cosine, I have a constant cosine term, a constant diffuse term, and a specular term that's defined by this formula, and I'm dividing it by this cosine theta I. That's how blend and foam material models are both defined. So if I were to draw this reflectance over here, what do I see? So I see that this diffuse term, this constant diffuse term, as just a constant value, right? So it's just a constant value over these all possible directions of the hemisphere. And the specular term is going to, it's again sort of cosine shaped, but it's to an exponent, and depending on the value of this exponent, it's going to take a sort of skewed shape. Of course, this particular direction that I picked here, that corresponds to a particular incoming light direction, right? So based on this incoming light direction, I'm going to have a specular term over here, and that specular term will change its place based on where my incoming light direction is, right? So when you look at this BIDF as a function of how light reflects off of the surface, you see that this is a very, very crude way of representing what could happen, right? So when you think about this as like, having a very complex surface, and from this complex surface, I have light reflectances in all directions, and I have this statistical distributions of light reflectance in all different directions. This is a very crude way of representing this really complicated function and this really complicated light reflectance behavior. I have just one constant term and just one bump. And depending on how you set these parameters, it might look okay, but when you put it in this picture, I think it sort of makes it very clear how simple this blend foam material model is, right? So you shouldn't expect it to produce some really realistic looking materials, even though it actually works okay in a lot of cases. Another thing that I would like you to recognize here is that a lot of times people look at blend and foam. It's not a physically based material model, yes, but they say that it's not energy conserving, and that is true. But I would say it's not necessarily energy conserving. For example, the particular parameters for the diffuse reflectance and specular reflectance that I asked you to implement in the upcoming project, well, the project that you guys are implementing or have already implemented, the particular parameters that I suggested in the project description would produce a very unrealistic material model. Because I said, this is going to be white, that is 1, 1, 1. This is going to be white, 1, 1, 1. that means I'm reflecting all of the light diffusely, which is on itself ridiculous, because if it is 111 coming out of all directions, even the diffuse reflectance itself, just diffuse reflection, forget about specular, just diffuse reflections itself is going to reflect more light than it receives. Really? Yeah, it really does. Because if I take an integral over the entire hemisphere, I just have this diffuse value, it's constant, 111. What I'm going to get is going to be the area of my hemisphere, right? And the area of a hemisphere is what? Area of a unit hemisphere is? Yes. So we're going to get this 2 pi term. But we have this cosine term here, multiplied by this cosine term. And if you include this cosine term, you will see that we're going to have a pi term in there to be able to normalize this diffuse reflectance. So just putting 111 white as the diffuse reflectance is going to produce too much reflectance off of this surface. Alright, so let's say that we scaled it down. We kind of need to be careful about this specular reflectance term as well. And in this case, it depends on what this exponent, the shininess parameter here, this exponent alpha is as well. As this alpha gets smaller and smaller and smaller, then this reflectance area is going to get larger and larger. This specular reflectance area is going to be larger and larger. That means I'm going to be specular reflectance over a larger area over the hemisphere. So I need to pick a smaller and smaller reflectance for this specular component here. But when my alpha is larger and larger, I have shininess value that's closer to infinity, then I'm going to have a very sharp spike at one point. Not maybe 1 point, but maybe shiny spike at close to 1 point here, close to one direction, one perfect reflection direction. So my specular reflection coefficient here can get larger. Right? If you want to have an energy conserving material, a material that does not reflect more light than it receives, you kind of need to be careful about how you set this diffuse and specular components. And how you set the specular component will depend on how you set this exponent alpha. Right? And so a lot of times, actually, in some applications, people will tie the value of the specular constant here to the value of this exponent. So as you change the value of this shininess parameter, that software might automatically scale this value. So as you get a wider specular lobe, everything is going to be lower, and if you get a sharper specular lobe, you're going to have a stronger specular reflection with a larger magnitude. And of course, you know that if light is reflecting diffusely, that means it's not reflecting specularly, so you kind of need to be careful about how you set the two of them together. So there's some work on energy conservation, how you handle blend and foam materials, so you get energy conserving materials. But I'm not going to get into that, but I just wanted to give you the general idea of why this is we're going to talk about why this is an important thing. But at the moment, I'm just telling you that this is an important thing because we don't want materials to be reflecting more light than they receive. All right. But nonetheless, this is a very, very simple material model with a very, very simple shape. In reality, like we have a whole bunch of material models in computer graphics, and there are different considerations when you come up with a material model. Your material model is going to have some parameters so it can represent different types of materials. So if you find this too crude and not realistic enough, you'll probably have more parameters to adjust for a more realistic material model. And probably the function is going to be more complicated than these simple cosines. So it could be a more complicated mathematical function. And in the end, is that going to be realistic? How realistic it's going to be? It's going to depend on what kind of model you use for generating your BIDF function, right? So the best thing we can do if you want to get a very realistic looking image, what we can do is that we can just measure this. So I can just shine a light on a surface for all directions, and then I measure the reflected light for all directions, and I can actually measure the value of this BIDF function. Now I'm going to show you some examples rendered using measured BIDFs. So this funny shape, I don't even know what it is, but it's an interesting looking smooth shape. It's eliminated by some, we talked about this image-based lighting, right? So it's illuminated by an environment map that's light is coming from all directions with different magnitudes defined by an image. And the right reflectance computed on these surfaces are coming from some measured BIDF models. So you can think of this as like a tabulated values for this 4D function being the BIDF. And there are different ways of tabulating these values, different material databases. They represent their materials differently. So this is showing some renderings of the different materials. So these may or may not look very realistic to you, but at least these materials look exactly like what they're supposed to look like if they were observed under this particular illumination. Another thing that you should consider is that if you look at the blend and foaming material models, those are what we call isotropic material models. So the specular term is not going to vary too much depending on from which directions you're looking at the surface. So we say we're defining them based on the directions of incoming light and outgoing light. But as we rotate incoming light and outgoing light's directions around the surface normal, we might get different reflectance properties for different materials. So some materials look isotropic, like this example over here, and some materials look very anisotropic. So it's almost like this specular term changes as you take the object and rotate it. So some materials will be anisotropic, and the specular reflections, specular highlight on that surface will change its shape accordingly because of this anisotropy. Now I'm going to show you some examples here, some different material models. These are rendered using a compact representation of some measured material models under an environment illumination like this. Different material models, and the reason why I picked these particular images from this paper here, from video of this paper here, is that see, like, this is a very anisotropic material. So as the light rotates and the surface is illuminated from different directions, it's not just the specular reflections change their places, but they're also their shape changes quite a bit, right? So you see this plate has some very anisotropic specular reflection profile. And we have analytical models for representing such anisotropic materials, but we also have measured BIDFs that represent this anisotropic behavior of the material model. So in that case, the reflectance does not only depend on the surface normal, but also how the surface is oriented around that surface normal. So you get the anisotropic direction correctly. So that shading becomes a bit more complicated for those materials. All right. So this is what I plan to talk about for today, just to give you guys a general idea of what rendering is and what rendering equation is. Next time around, we can continue talking about rendering. All right then, I'll end it here. Thank you all for joining us, and I'll see you all next time.